Hello everyone, welcome back to the ExpertFunda. So today we are solving a really interesting problem that is based on the graph problem, network recovery path. So during the contest, I have already provided you the solution, but I have not gone through the deep dive. I have make you understood that what the question is saying that, right? So if you have already gone through the video, so it will be better for you to understand better. Okay, so please go and watch that video, then come to this video, so you will understand very logically. Okay, so why I have created this video. But still, if you don't want to go, you can continue this video because I have gone through in very basics, so that you can understand how this network recovery problem you can solve, right? And how we are solving using the binary search and the topological sort. Okay, so by the end you can master yourself this problem, and you can work on any problem which is coming, like network recovery pathways, right? It is coming in the you can say in the graph problem, right? So you can solve. I'll also provide you the couple of videos which is similar to these patterns, right? So you can also try the Leetcode problems and other portals problem that is based on these problems. Okay, because this question is really important for you, and the sets of questions that I will provide you at the end, that is also very important to do practice to understand how this type of network recovery path, or you can say the graph problems, works in the contest or in the during the exam. Okay, so let's understand. So very first, what you need to do, so we have given a network recovery path, that is we are given a directed acyclic graph that is called DAG, and the nodes we have given is n nodes, means 0 to n minus 1s we have given, right? And we have given a list of directed edges where each edge has a recovery cost. And if you say we have given a online array, it is a list of what we call nodes, means some nodes are offline and you can visit online immediately, intermediate nodes, right? So all the nodes which are online, right? So all the intermediate nodes are what we call is online, so you can visit it. So we must go from node 0 to node n minus 1 that we have seen yesterday in the example. Okay, it means you are given a directed cyclic graph with n nodes, right? And n nodes means 0 to n minus 1 nodes, right? We can say, and each directed edge has a recovery cost, and all those costs are given to you in the edges, right? And you can also say some of the nodes are offline, right? And we are only allowed to travel through the online intermediate nodes which are online, right? So what is our task? Your task is to find a valid path from 0 to n minus 1 where all the indeterminate nodes are online, and the total cost of the path is less than equal to k, that we will see later. And you want to maximize the smallest edge cost in the path, and that is called the path score. If no valid path exists, we will return -1. Okay, so see, so the valid path is a path from 0 to n minus 1 is a valid path only if all the intermediate nodes are online, sum of edge cost, the path is less than equal to k, and the path must be direction of edge. So what is our goal? Our goal means among all the valid paths, right? There we have given the you can say the graph, and from all the valid path will be there, right? So we have to find one where the smallest edge cost is the path is as big as the possible, and this smallest edge cost is called the path score. And we want to you want to return the maximum path score which is possible. So if no path is there valid, will return -1. So let's understand the example we have given here. So example is saying that we have given input, right? Input edge is 0, 1, 5, 1, 3, 10, like this we have given inputs, and these are the onlines we have given, means we have given edge we have given, online we have given. you know what is the age is 0 and 1, right? So if you see this graph, what we have given 0 and 1. What is the cost? We have given cost is 5, right? Again we have given 1 and 3. What is the cost? 10. So like this we have given all the ages that we have already discussed, and these are the what you call node is online or offline. So in this case all the nodes are online, not offline. And k is 10, means as we understood that path A, we have seen already this example, but still let's, because this is a new video, maybe some of you are not going to see the another video, so understand path A, there is a one path, we can say path like this from here to here this way, and this is called 0 1 and 3, and another path is 0 2 and 3. Can we see that path 1 path 2 means path A path B? So this path having age cost 5 and 10, can we say that 5 and 10, and so the total cost is 15. Okay, so if you represent in the graph, let's suppose if we start from 0, right, then we'll 1, then we'll reach to 3, right? Another path is 0 2 and 3. So either you will choose this path or you will choose this path, right? Means you will reach to the destination from 0 to n-1, you will reach there, but we have to find all those valid path which is less than equal to 10. But if you see the age cost is 5 and 10, if we do the total, it is coming 15, which is less than equal to 10. No, right? In that case it is too costly, we'll say it is invalid path. Then we'll go with the path this, and you will do the same thing here. So the age cost is 3 and 7, you can say 3 and 4. If we do the sum, we'll get total is 7, and this is within the k less than equal to 10, right? 7 is less than equal to 10, it is valid now. So this path is valid, so this path will say valid. Now we have to find the path score. What is the path score? It should be the minimum of all the given age cost, right? The question was saying, so will 3 and 4 will take, which is the minimum? 3, and so the answer is 3. We have selected this valid path. So among all the valid paths, there will be multiple valid path, right, in which we have to take the one of the path score which is minimum, and that will return here. Okay, so what is the tricky case here? Let's, for example, we have given these ages we have given, and some of the all the nodes we have given is online, and k is we have given 36. So if we'll represent this graph, right, the possible path is there is 0 2 and 3, right? So if I'll go with 0 2 3, total age cost is what? You know that 2 and 3 we have cost is 22, right? And 0 and 2 we have is 4. Can we say that? Means yeah, correct. So if we'll take 0 2 and 3, 0 2 is taking 4, and 2 and 3 taking 22. So this 4 and this 22, if we'll add it, it will get what? 26, and it is less than equal to 36. We'll say this is valid, right? And so we'll find the mean cost. If we'll find the mean cost, mean age, we can say it is 4 between that. This is what 4 and 22. What is minimum? Score will become 4, right? And so answer is coming 4. If we'll take another one, right, it will 42. Let's suppose we have 1 2 and 3. So here from 1 and 2 we have given what? 42. So itself is greater than 36, no need to add further, right? If we do 22 plus, means 22 plus 42, it will come out 4 and 62, we can say 64. So 64 is not less than equal to 36, so it is invalid. So there is only one path. So you have to understand these cases. So let's summarize this. You search all the possible, right, paths 0 to n-1 paths, we can say that, right? Each path score is what? The minimum age cost along it, right? Only consider path that use only online intermediate nodes whose total age should be cost less than equal to k, that we have seen in the tricky part, right? We have to return the maximum score you can find, right? What is the maximum score that you can find? Means you have to find all the valid paths, and from there you have to find the article cost score, right? And whose score is less than equal to k, means that is valid path, right? and then we'll find the each score of the each valid paths, right? And from there you have to find the maximum score that you can get. So what is our goal? Our goal is to find the best path from 0 to n-1 in such a way all the interview nodes are online and its cost should be less than equal to k, right? So it is also saying among such path, pick the one with the highest path score, which is equal to minimum path cost. Can we say that? So now let's understand the intuition behind the problem and the approach, right? So as we know, the intuition is saying that we are working on working with a DAG from 0 to n-1 nodes. So our goal, we have to find a path from 0 to n-1 node, right? So all the interview nodes are online. The total cost of the S should be less than equal to k, and among all such path, we want the one where the smallest S on that path is as big as possible. So the smallest S is the path score, and so our job is to maximize this score. So what we can say, each path has a path score is equal to minimum S cost on the path. So to minimize the score, we want the path highest minimum is S and the total cost is less than equal to k. So all interview nodes are online. Can we say that? So what is our core idea? Our core idea is to use the binary search on the minimum S value. So why we are going to use binary search? Because if we try a candidate score k, right, score x, we can say filter out all the A's with the value less than k, right? And then x. So then we'll check if the valid path exists which is less than equal to the total cost of the k. Can we say that? If the total cost less than equal to k, if it does, we can try a higher score and we'll try to maximize that. If it doesn't, we need to try a lower score. Let's understand an example. Very first, what you need to do, binary search will do over the edge cost. We'll take low and high, as we know that. We'll try the minimum value. Wow, mid equal to low plus high by 2 as the minimum edge we want on in path, our path. So for each given mid, we'll try only edge which cost is less than greater than equal to mid. Then we'll check is the path is there from 0 to n-1, right? If the cost is less than this and all are intermediate are online, then we'll say yes. We will say yes or no here, right, with the path. Then we will use topological sort plus dynamic programming to do this efficiently on the DAG. So why we are going to use the topological sort? Because topological sorts DAG allows topological order. Each node is visited only after its dependency, right? Using this order, we can relax edge like etc., but faster for DAGs. Okay. If you're not aware with the topological sort, let me know in the comment section. I'll create another video so you can understand how it works. So do we about topological order, we will use a cost, right, where cost at I equal to the minimum cost to reach node at I from node 0 using the valid filter edges. So for each edge u to v, what will happen if cost at u will do plus edge cost and it should be less than the cost at v, it means we will update it, right? Means finally we'll check cost at n-1. If it is less than equal to k, we'll return the value. If yes, path exists for the mid value, we'll search for the higher score, and else we'll search over the lower score, right? So if we will summarize this, so very first what we need to do, we'll do the binary search on the score mid edge value, right? And for each candidate score x, we'll filter the edge with cost greater than equal to x. So do a topological sort, right, and with the DP to find the smallest path cost, you can say from 0 to n-1. Then we'll check if the path cost is less than equal to k, and only we will use online intermediate nodes. If yes, we'll try the higher x. If no, we'll try the lower one. Okay. So if we'll talk about the complexity, right, time complexity, the binary search we have is O log max is, and we'll provide the, let's suppose for 030, right? So for each binary step, right, we know the max age is 30, that is why we'll take here. Okay, so for each binary step we'll filter as O of m and we'll do the topological sort plus dp, it will take O of m plus n. So the total, if we'll say, we'll just add this O m plus 1 into log max s. Okay, it is very efficient for the larger input because we have given ages up to 10 to the power 5 ages and nodes can be 5 into 10 to the power 4 nodes, right? So for in this case larger graph, it is very efficient. So if you have gone through the code study that I have uploaded, so what we have given as we have given, then we have given online, right, where all the nodes are online or offline, and then we have k that we will check the score should be, the sum should be less than equal to k. Now we have n, right, we'll get the number of nodes, initialize the graph, and graph value we will initialize, or as each index we will initialize here, so that from each edge we'll get the s and we'll fill the graph. Can we say that? Means we are initializing the graph, we can say that. Graph is ready to use. Now we'll do the binary search, so we'll take int low at 0 and high will be at here, right? It's a 10 to the power 7, we can say that, and answer is -1. Why we are taking, you can see the constant that in the problem, right, and you can understand why we are taking that. Answer is at -1. Initially we have initialized, so we'll go with low is less than equal to high. We'll find mid is equal to low plus high minus low by 2, and you will get the mid. You know the binary search, right? So we'll check once we'll get the mid, right? It means we'll check if it is valid, right, path. So we'll pass the graph, online, k and mid, right? So from there we'll pass the what you call this mid, and we'll check is it valid. If it is valid, we'll update our answer, correct? And as well as we'll find the low, so we can have the mid plus 1, and it will increase, it will go to the lower side, right? Because we have to find the minimum, right? And then we'll have our low here updated. So you will say why we are using this binary search, right, on the path score, right? So we want to maximize the weakest edge in the valid path. So binary search the value of the mid edge cost, right, and the minimum is that must be present in the path. So we are trying the values from 0 to 10 to the power 9, we can say, right? So at each step we are checking if the path exists. If the path exists, means this path is this path is this a valid path exist, right? So if this valid path exists, using only when edge is greater than equal to the mid edge cost, right? Means the edges we have right should be that I'll show you this method, right? Means where only edges greater than equal to the mid edge cost, right? That is valid, right? So we'll say we are checking at each step, we will check, right? For example, let's suppose we are trying the mid edge is 4, right? Mid edge cost is 4. Then we will check, can we reach to the node 3 from 0 using the cost given the cost edge cost greater than equal to the 4, right? If it is yes, right, means we will say we are having the valid one, right? And does the cost stay is less than equal to 36? Like that we will think, and we'll have our binary search over the path score. Can we say that? So the is valid method, what it will do for each binary search, right, the mid edge cost, we can say what will happen, we will build a filter graph, and only the edge with cost greater than equal to the mean edge cost, we can say. Let's suppose we have mid edge cost is 4, right, and we have some edges. Let's suppose 2 and 3 was 2 and 3 having 22, right? So it will check is 22 is greater than 4, right? If it is greater than 4, right, means we will include that. Then we'll check what 0 and 2 having the edge cost is 4, right? So we'll check 4 is greater than or equal to 4, right? So greater than or equal to 4, it is also say yes. Then we'll check 1, 2 and 42 was there, right? So if 1 and 2, we will take the note, is it greater than 42 is not greater than or equal to 4? Can we say that? So 42 is greater than or equal to 2. It means 22, 4 and 42 all are greater than what you call the 4, right? And so for the mean cost equal to 5, we'll say cost is 0 to 2, means cost 4 is included, means it is valid. As we understand, I have gone through the example also, right? Now understand how we are going to use further, right? So let's go to the next. So this is your what you call valid method, where we will do what? We'll filter the what you call the list, right? We'll filter out and we'll check. We'll go with all the cost, right? And we'll check the mid cost is there, right? Then we'll filter it and we'll add here, as I told you, right? Means we will check the cost. If it is the cost is greater, let's suppose this is what you call 22, 4 and 36. If all are greater than mid edge is 4, right? Means we'll add all into this filter list, right? Then very first step you need to do what? Topological sort we'll do for using the DFS. Means we will use this DFS to compute a topological order, means valid order of the nodes in the DAG, right? This will ensure us we always process a node after all its dependency. For example, if we have valid topological order for the graph, let's suppose 0, 2 and 3, right? So we can say 1 and 2 also, means total topological order. Let's suppose, give me 1 second, I'm saying let's suppose we have a topological order in the graph. Let's suppose we have order, let's suppose 0, then 2, then 3, like this we have, or 1 and 2. These are the valid topological order we have given in the example, for example, right? Means what is the possible topological order for this? So let's suppose one of the possible is 1, then we'll say 0, then we'll say 2 and then 3. Can we say that? So this will be your what you call topological order, we can say. Okay, let's go to the next. Then we will use what? We will use the DP, right? DP will use on the topological order. Okay, so how we are going to understand? So very first understand that topological sort, how we are going to use. Okay, so as I told you, we'll create a topological order list, right? We'll go for all the nodes, we'll do the DFS, right? We'll check if it is visited. If it is not visited, do the DFS again, right? We'll provide the topological order visited, is it visited or not? Then we'll pass the filtered, all the filtered one, and the valid one, you can say, right? And we'll get our what do you call topological order added there. Okay, so all the topological order, possible topological order we will generate, and then we will do in the reverse order. Okay, then in the next step what we need to do, we'll use DP on these topological order once you got it, right, to compute the mean cost from node 0, right? So how we are going to do? Let's say very first we'll create what you call dynamic programming, right? For the dynamic programming, we know that we need something. Let's suppose we'll call distance, right? And we'll add the default value, let's suppose 0, right? So we'll fill all the value initially with the max value, and dist at 0 will fill at a initialize at a 0, right? And we'll iterate over all the topological order. So what we are trying to do here is we want to compute the dist at I, and this dist I is nothing but the mean cost to reach the node I, let's suppose, to node 0, from node 0, right? We can say. So if dist at I you are taking, right, it means the from the what you call node I to node 0, what is the minimum cost? Understand? Okay, that we will keep storing, right? So initially we'll initialize as a 0, right? And then we'll go to 1 to n-1 node will go, right? And for that each node, what we need to do, we have to iterate over this loop, right? So then for each node u in the topological order, what we need to do, for every edge that is happening from u to v, right, we'll find the cost c. Okay, and if node n is offline and no start and end, we will skip it, otherwise we'll update it, right? How? Let's suppose if it is, as I told you, if it is what you call, you can say offline, or there is no start and end, right, we will continue, right, we will not do anything. Otherwise we'll check its edge, right? We will check the edge, we'll get the edge from filter u, right? We'll get the edge. For every edge, right, you will have our cost, right? So what you need to do, you just check if it is not equal to it is offline, right? It is not online. First of all, check if it is offline and there is no start, right, or end, right? It means we have to escape these intermediate offlines, right? And then we'll update what is the previous value of the du, right? And then the cost, right? You know the cost, previous cost, and this is the thing, right? So you want to update this value because we have to check with the dist at v, right? So then after, what we need to do, we will update our dist at v. If it is less than, means the minimum value we have to update, right? And for that, if you are updating that this value is coming minimum one, so we'll keep checking the max value and mean value. If it is a mean value, we'll update the mean value here. Okay, I hope you understand, right? At the end, at the final thing, what we need to do, we'll find the what do you call, the valid one. If it is the path is what do you call, if path is valid, right, then we will check the sum. We are storing the sum here, right? If it is less than equal to k, it means we have checked that the binary search was giving what value, right? And we are storing only if it is yes, means if it is higher cost, we'll update the cost. If no, we are using the lower cost, like that. So we'll store all the values on the dist, right? And then finally we'll check this condition and then we return the value. Okay, so it is it's easy, but you have to focus how to do that. Now understand what we have here. We have visited u, right? And then we have this graph we have, right? Graph at u will store the value here, right? And we will iterate over all the edges, right? We'll check if it is visited. If it is not visited, then visit it and get the topological sort order updated, right? We will update it here and will not return, but we will keep updating here. The very first thing, now you will say, one of the comment I have shown in the previous video, that how you approach this problem, right? So very first, you try to understand the core objectives. What we have given, we are given a DAG, right, with a weighted edge. We have path cost we have given, which is less than equal to k, and our requirement is to maximize the minimum edge on the valid path. So this smells like a binary search on the answer problem, because we are trying to maximize the property that is called mean edge under some constant, right? It means we have to recognize the pattern, right? And then we have to optimize it. So if we can ask, can I make the score at least x, we can write an efficient function to answer that. Then we can use binary search on the answer. In this case, can I find a path from 0 to n-1, means the cost should be less than equal to k. With the cost less than equal to k, means only s greater than equal to k, x. So answer is double. So what we need to do, we need a graph traversal with a constant, right? So now we will realize it's a drag, right? So that's a very huge because it's a drag. So we can do a topological sorting, and then we'll use DP programming over it. And if there is no cycle, no etc needed, right? Because it's expensive. Then we'll check add a path cost and online node constant. So we have the DP or traversal window. So only process the path the interim node is online, and maintain a cost at I array to track minimum cost to reach each node, right? And that will give you the constant DP plus topological sort setup. Then we have to build the final algorithm. Let's suppose with the binary search for each mid value, we have to filter the S be the cost greater than equal to mid. Can we say that? Then we'll run the topological sort or plus TP, and we'll check if this value matches. If it is the condition true, return it. If yes, we'll try the bigger mid. If no, we'll try the smaller, right? This is the concept that we have seen in the algorithm. So now you can say that how I know this, that we are going to solve it, right? Because I have seen similar problem, right? Let's suppose if you have already seen minimum and maximize the path. So this is Leetcode problem where you can understand how to minimize and maximize, how to minimum the maximum path, right? Problem that you can see and understand the pattern. This is another problem is widest path or bottleneck path you can try, and there is a concept of binary search and the feasibility check, right? And the tag constant we have to use, and topological TP concept we have, right? If you want to practice, right, there is a list of questions we have, right? You can try by yourself to practice this type of questions. So these are the questions we have, right? You can try by yourself. Just do Google search, you will get all the details of these questions, or let me know in the comment section that I can provide you the details. Thank you guys, thank you for watching this video. I hope you will like this video, and if you have any doubt in this video, let me know in the comment section. Thank you guys, thank you for watching this video. I really appreciate your time to see the video, and please write the code by yourself so that you can understand clearly, okay? But still, if you have any doubt, let me know in the comment section. Please like and subscribe ExpertFunda. To support ExpertFunda, you just need to do a like button and do subscribe, and also click on the bell icon button so you can get the updated videos. Thank you guys, thank you for watching this video.